specialist for all these kind of high-speed transfer systems and solutions. I would like to introduce first what we are doing today, what we will discuss. I will give you an overview about the general applications of a high-speed transfer device, and also especially what is the main task of such a solution and the device, and what is the difference to main ATS, which is very well known as an automatic transfer system, makes also transfer, but what is the big difference between these two solutions? Next step will be what you need, necessary components and preconditions in your switchgear and voltage transformer and so on. Then we step over to the construction and the interfaces, what is necessary to integrate such a high-speed transfer device into a switchgear. The different variants, high-speed transfer devices are available in different variants to fulfill different solutions for different kind of switchgear applications. And how a HSTD, I make the short word HSTD, high-speed transfer device. It's a little bit easier to spell all the time during the presentation. I will show you the main thing of this device, the different transfer modes the device will perform to different kind of network situations in the moment of initiation. So let's start with the high-speed transfer device, the philosophy. What are the benefits if you use such a device, the construction, and last but not least, important thing, the functional modes. You are all experts. You know what is means by interruption of the power supply into a power plant or industrial plant. You have big loss of productivity. You have this huge downtime. You need a lot of time to restart all the machines, the robotics, the conveyors, the kilns, and so on, the extruders. So you know how long this takes and how much does it cost. You have made damage on production equipment if you've lost the power, damage on your products which you are producing, delays in delivery for sure, and so on and so on. You know all these kinds of problems occurring if you lose your power during the normal operation of a plant or industry or chemical plant or oil and gas. So therefore, there is a solution. The high-speed transfer device ensure a nearly uninterruptible power supply to all these important loads by a transfer from a main feeder to a standby feeder. And the transfer will be done so quick that you will not lose your load on the bus bar. That means you have no interruption on all the connected processes. This is also the big difference to an ATS. In ATS, you know, makes if there's a failure, for example, in this main feeder, this breaker is normally closed. It's open. Then wait a certain time, a second, 2 seconds, and then close this feeder. So after 1 or 2 seconds, you lost all the connected processes and all the connected loads. So it must be restart everything again. You have not really a benefit. With a high-speed transfer device, it's a big difference. With this device, this will be opened and this will be closed so quick that you have no interruption on your power supply on the bus bar. This will be explained later on very in detail how does it works and how such a HSTD can do the transfer so quick without any problems to the connected loads. So the second task of this high-speed transfer device is also to protect during this transfer all the connected loads and to do the transfer so quick that you have no interruption on your processes. Yes, as discussed now, you have this high power quality with such a device, uninterrupted power supply during this very fast changeover procedure. Yes, permanent availability of the electricity. You have no more breakdown. You have no more the outages, the time for restart everything again. So if there's a failure on the incomer, you lose the power. Even if there's a failure on the transformer, or you lose your network from the high voltage to maybe to the transformed medium voltage. So is there any interruption? This will be change over to a standby feeder. And this will be done so quick that you have no more interruption. Where can you use such technology? So you can use it everywhere where you need an uninterrupted power supply. So that means normally in power generation, this is one of the main fields of this application. Nuclear power plants, distributions, in industrial power plants. So you can see it everywhere, and also in plants with sensitive load, like with robotics and conveyors and so on. You can use it everywhere where a connected process is included, and you have to ensure that you will have never interruption on these processes. So now the question is, such a device, very good, I can use such a thing. So what do I need into my switchgear? So you need a high-speed transfer device, a HSTD, and what you need is the existence of two should be independent synchronous feeders. This means the main feeder, which normally feeds the busbar, and the standby feeder, to where we can make the changeover in case of a failure of the main feeder. So they should be in synchronous condition, means no constantly phase angle difference between main feeder and standby feeder caused by different kind of transformers. Next, circuit breaker. We say, okay, for HSTD, which makes a transfer very, very fast, you need also good circuit breakers with short operating times. So short operating times, we say below 100 milliseconds. So state-of-the-art breakers, from today needs maybe for opening 50, 55, 60 milliseconds, and for closing maybe 10 milliseconds more, means 60, 65, 70 milliseconds. The circuit breaker state-of-the-art since last 50, 20 years. So, and also older breakers could have also very fast times below 100 milliseconds. So that's necessary. If you have very slow breaker, then it makes no sense to have a high-speed transfer device. So must fit together. Then also the next is a load configuration, means on the bus bar with a certain kind of rotating devices. Later on we'll just explain very in detail why you need these rotating devices. The rotating devices feed some energy back to the bus bar during the transfer. This is only for a few milliseconds. Later on we see very detailed recordings from transfers, and then you can see how does it works when the rotating machines working and acting like a generator in this moment of the transfer to stabilize a voltage on the bus bar. And also what you also need for high-speed transfer device, a high-speed transfer device is not a protection relay. So the transfer device will not detect the failure in a network. Means if there's a failure in the main incomer, this must be detected by a normal protection system, which is normally also included into the switchgear, which is already existing in plant or something else, and gives the information to the HSTD. There's a failure. Please perform the changeover. Could also be information like temperature from transformer is too high and we get a problem in the next 3, 4, 5 minutes or shorter. Then also you can give information to this device, and the device will make the changeover without any interruption to the connected processes before maybe the transformer go offline. So there could be many kind of initiation criteria to start this transfer. Once more, there's some interfaces what you need. We need the interfaces to the circuit breakers. Yeah, for sure, status and control, that we see it's in operation, it's in service or something else, that we see the status and can control. HSTD devices also control directly the circuit breaker without any auxiliary relays in between. The HSTD needs also the voltages from the main incomer, from the standby feeder, and from the bus bar. And optional also currents. Normally you need the currents only for commissioning. I will explain later why. For the normal operation, you need only the voltages. You need the external protection signals. That means the initiation of the HSTD. Initiation means there's a problem, please perform the changeover. And optional, like every kind of devices, the connection to the DCS. So this is a usual block diagram from such device, but I want to point out the heart of this thing. And in here I explain a little bit how the philosophy of this device is. The device, high-speed transfer device, the name must be high-speed. And in this moment we take all the measurements all the time from the voltages, from the main incomer, from the standby feeder, from the bus bar. Such a device calculates synchronism, phase angles, frequency differences, voltage levels, and so on. And this will collect all the data all the time. And with this data will be there will be a kind of, yes, I would say, we take this all, see what the network status is, and make a decision in this moment which kind of transfer mode we would perform in the moment if we get in this moment initiation signal. So that means all the time the device measures, calculates, and have a result. The result is one of 4 different transfer modes. I will explain later on. One of 4 different transfer modes, and the result is always given. That means if we get now initiation signal, we know this result and can act directly one of the 4 different transfer modes according to the network situation in the moment of this initiation. If we would do it in other way, that means we get the initiation signal, then we take all these measurements, calculate, and get a result, we're losing time. And to avoid losing time, we do it all the day, all the time, every second, take all the measurements, make a calculation, and have a result. That means always a result is known to the network conditions. And if the initiation signals come, the device can act directly without losing any time. There are some, so that you get some idea what we're talking about, size and how such a device can look like. This is a low voltage compartment of medium voltage switch bay, and you can see the dimensions of such a device. It's about, I would say, 35 to 35. It's a cubical centimeters and a weight of about 10-12 kilos. And you see this is about the size of such a device installed in the low voltage compartment. Also, a high-speed transfer device has also a HMI to control, to see status. And here you have an example if this device is included into a cubicle. So these are only some examples that you get a feeling how big is this device and how many connections we need. It's very easy. So such devices are available in different kind of variants. The variant means, yes, the application field to the switch gear and network configuration. You see here, this is very common in many kind of power plants. You have one bus bar, you have one main feeder, and one standby feeder. And here are the loads connected, made the important loads to keep all the processes alive. Then if you have a failure here on the main feeder, this device will immediately open the main feeder and close the standby feeder in the transfer mode, which is according to the network conditions in the moment of initiation. This will be explained later very in detail. So that means failure here, open this one, close this one as fast as possible, and in the fast transfer mode, all the loads and all the processes will keep alive. You will have no interruption. Variant 2, also very common. You have two feeders, two bus bar sections, and a bus bar coupler. These are normally closed. This one feeds this bus bar section. This feeder feeds this bus bar section. For example, you got a failure here. This one will be open and this one will be closed. And everything will feed by the healthy feeder to both bus bar sections. Now, sometimes you can say, oh, this may a problem. The transfer is okay, but this feeder has not the capacity to feed both bus bar lines. Maybe it's not strong enough. So in this moment, also HSTD devices has the providing load shedding signalization. That means you can give load shedding signalization to main motors or something else, which are not so important for the connected process. And then in the moment of transfer, you can disconnect some not important loads that the second incomer will not can provide energy to all the other loads. So, and if you have this normal configuration, you can make the change over from here to here, means open this, closing this. Or if you have this and you have a problem here, the breaker will here be opened and here closed, and everything will feed from this other side. You can see here two boxes. This is always in the middle. It's one HSTD. It's one HSTD. For all the different variants, you need only one device. One device can control up to 3 breakers. Now we step over to the variant 3. It's similar to the variant 1. You remember you have one main feeder, one bus bar, and one standby feeder. But in this configuration, you have 2 available standby feeders, and you can make the decision with a pre-selection to which standby feeder the transfer should be performed. That means if you have a problem here, this will be open, and according to your pre-selection, this breaker will be closed or this breaker will be closed. Variant 4, you see, it's also very similar to the variant 2. We can perform transfer from here to here, means you have a failure here, open this breaker, close this breaker, everything will feed from this side. Or, this is closed, we have a failure here, then this one will be opened, this one will be closed, and everything will feed from the other side. But the variant 4 has one more feature. After a failure, this one will opened and this one will closed. Everything will feed from this side. Situation is closed, closed, open after this transfer. Now this feeder gets healthy again, but in this moment you got a problem on this feeder. And then we can perform also a transfer from here to here. That means, once more, closed, closed, open. This one is healthy again. Here comes the failure. Then we open this one and close this here. Then everything will feed from this other side. So you have every kind of possibility to make the changeover from here to here, from here to here, and also from here to here. This means an extension of the variant 2. And the variant 5 is also the extension of the variant 3, the one main incomer, 2 possible standby feeder. You can make the pre-selection to which breaker should be performed the transfer. But this one has also automatically system inside that we can perform transfer from here to here, from here to here, or from here to here, from here to here. So in every kind of direction, transfer will be performed always with the main aim to keep all the loads on running. That means if there's all 3 available and you have on one feeder a problem, then we will change over, and then we have here a problem, then we will make a change over to here. So you can lose 2 of these 3 feeders without any problem to your connected loads. And in combination of more than one device, you can also match to huge switchgear configuration with 10 incomers, 5 busbar coupler, and so on, and use more than one HSTD, and you can fulfill transfers in every kind of direction. There's a bigger overview that you can see once more how such a HSTD will be integrated. Everything is already at site. The breakers is at site, all the voltage, the protection relays, normally at your switchgear, at your facility, at your industry. So, and if you include a HSTD, we need the information from voltage from both feeders. We need information from the busbar voltage. We need a connection to the breakers. And we need initiation signal from the protection relay. And this is how it looks when such a device is integrated into your switchgear. That means protection relay detects a failure, gives the initiation to the HSTD, and also give a trip signalization to the breaker. HSTD also gives a trip signalization to the breaker and makes a decision to which special time this breaker will be closed. This is one of the 4 different transfer modes. Normally, you have the fast transfer mode, and then it will be opened and closed so fast that you will not lose your process. I hope so. Up to now, it's more or less everything clear. Transfer device, very fast changeover with different variants to different kind of switchgear configuration with with 2 breakers, with 3 breakers, with 1 busbar, or 2 busbar sections with a busbar coupler. Now we step over to the more theoretically thing, to the transfer modes, which makes the really big difference to an ATS. ATS opens the main feeder, waits a certain time, 1-2 seconds or something else, and then close the standby feeder. So you will lose everything, you have no benefit. So with the HSTD, we have the 4 different transfer modes, which I always named before. We have the fast transfer mode, the transfer at first phase coincidence, the residual voltage transfer, and the time-depending transfer. But first, I would like to explain a little bit what you can see here. This is made at the beginning confusing, so much lines, and here's the time, phase angle, here's voltage. But we go on now step for step. It's really important to understand how the device, such a device is working, and what are the situation for the different kind of transfer modes. As I explained, the device measures all the time the voltages, makes the calculation for phase angle, for frequency, for synchronism, and so on, and have this result all the time. And the result is one of the 4 transfer modes, and we have always this result. If we get the initiation, we can act directly. So what you can see here on this line is the phase degree. Here we have a timeline, and here we have busbar voltage. Here is a line which I now explain. If you have, we make it easy. We take this configuration 1 busbar, one main incomer and a standby feeder. So what has happened if you lose the main incomer? That means no more available. Breaker is open, maybe transformer is no more longer online, you can say online in this moment. Then this is like the main incomer is open, the breaker, and the standby feeder breaker is also open. Then a bus bar is isolated. In the moment the bus bar is isolated, we have all these rotating machines on the bus bar. In the moment a bus bar is isolated, the machines are running with high speed. In this moment, they're acting like a generator. They feed they're feeding energy back to the bus bar. They're declining with the speed. Bus bar is isolated. Yes, both breakers are open from the main feeder and from the standby feeder. They're working as a generator. They feeding some energy back to the bus bar, stabilize the voltage on the bus bar, but they're running slower and slower and slower. Yes, and this is what you can see here. In the moment of isolating of the bus bar, the voltage on the bus bar is declining in the same way like the speed of the machines are declining. Yeah, they're acting as a generator, but they get slower, slower, slower up to a stillstand. So this takes to the motors and to the application, it's a fan, it's a pump or something else, more or less longer, maybe 100 milliseconds, maybe a half second. On very big machines, on fans, they're running 2, 3, 4 seconds. And then with big machines, this line will be go so. And with small machines, you can imagine they are running very fast, but they declining very fast also. And then this line will be going in this way, maybe. So in this example, the speed is declining, also the bus bar voltage is declining in this moment. And what has happened also? The machine's running with normal speed in the first moment, the bus bar is isolated, and then they're going down with the speed. And they feed back the energy to the bus bar with voltage. The voltage is declining, but also the frequency will change. At the beginning, 60 Hertz, and then it will be 50, 40, 30, 20, up to 0 Hertz when they get a stillstand. So, and if you make a comparison between the healthy standby feeder and this declining voltage and this changing frequency on the bus bar, we see this in the first moment they are synchron, the bus bar to the standby feeder, and then the standby feeder will have always the 60 Hertz, and then we have here 40 Hertz, 30 Hertz, 20 Hertz. But at the first moment, we have then a phase angle between, yes, standby and bus bar voltage. This will be at the first moment in synchron condition. Then it will be more, it will 10 degrees, 20 degrees, 30 degrees, 180 degrees. But at one special time, we have once more synchron condition. Later on, I can show you some picture how this looks like. And then we have the transfer at first phase coincidence. So this is shown here. Declining voltage on the bus bar, and also this changing of the phase angle. We have synchron condition, then we have no more synchron condition, and after 360 degrees, we have a special moment of once more synchron condition. But to avoid some confusing, we will start with the fast transfer mode. We need some preconditions. That means the network situation in the moment of the initiation for a fast transfer. That means they should be synchron. Fast transfer is allowed if the phase angle between bus bar and standby voltage is less than 20 degrees. The frequency difference is less than 1 Hertz. We have a standby feeder voltage of a minimum of 80% of nominal voltage. Okay, for sure. It makes no sense to make a change over to a standby feeder which is not available, because it's influenced by this failure from the main feeder, and the standby feeder is also not available anymore. So we say normally you need 80%. And also a bus bar voltage of more than 70% of nominal voltage. In this moment, we have a kind of synchron conditions for a fast transfer mode. And only at fast transfer mode, if these conditions are given, we send the commands to the breakers, to the main feeder breaker and to the standby feeder breaker at the same time, synchronously at the same time, but only at fast transfer mode. So, and what has happened if we send the commands to the breakers at the same time? Breakers normally opens faster than they closing. So we make an example. We send the commands at the same time. Main feeder breaker opens after 50 milliseconds and the standby feeder breaker closes after 60 milliseconds. So you see we have 50 milliseconds, 60 milliseconds. We have a time gap of 10 milliseconds. This will be shown here. You have this busbar voltage. Then here the failures appear. Then we get also the initiation signals to the HSTD. Fast transfer conditions are given. Everything is okay. Fast transfer mode is decided from the device. The commands are given to the breakers at the same time. So here the commands are sent to both breakers. We have a certain time for opening the main feeder. You see here this is the current from the main feeder. We have here this fault current. Here the breaker is open, normal current. Here is also the command sent at the same time, like to the main feeder, to the standby feeder breaker to close. And we need this time. Maybe this here are 50 milliseconds, and from here to here are 60 milliseconds. And we have this short time gap where the main feeder breaker is open, but the standby feeder breaker is not closed. So both breakers are open, busbar is isolated. And what is happening when the busbar is isolated? I explained before in the slide. The running machines working like a generator, and you see here the feedback energy from this machine to stabilize the busbar voltage during this transfer, during this small time gap, and stabilize in this moment the busbar voltage. This is made a better example. This is from a fault record during a transfer on a power plant. This is the main feeder, this is the standby feeder, this is the busbar voltage. In this moment, the commands are given. You see here, after 46 milliseconds, the main feeder breaker is open. He is also given the command to the standby feeder breaker. You see here the time a little bit longer. After 51.8 milliseconds, this breaker is closed, but we have a time of 5.8 seconds where the busbar is isolated. Now please have a look to the busbar. You see here, the breaker is opened, busbar is isolated, and you see exactly this is the feedback energy from the rotating machines during this time gap. And now overview to the busbar voltage, and you see nearly nothing. You see also nearly nothing during the transfer. So you can imagine you will not lose any connected load or process on the busbar during the transfer. The breaker is here open from the main feeder. We have this time gap. Here the breaker is closed from the standby feeder. And then everything runs with the standby feeder, but on the busbar you will have no impact during this transfer. This is the transfer for fast transfer mode. Only in fast transfer mode we give the commands to both breakers at the same time, means simultaneously to the main feeder breaker and to the standby feeder breaker. Only, I step once more back, only if these preconditions are given in the moment of initiation. Now it could be, this is the window of the fast transfer mode. This is the voltage from the busbar, the phase angle, this is shown here with the 70% of the busbar voltage, with the maximum 20 degrees of phase angle, then we have the fast transfer mode condition. So, but it could happen if the initiation signal comes too late. Then the bus bar voltage is below 70%. Then we have no more the conditions for the fast transfer. Or the phase angle is more than 20 degrees. Then we have no more this kind of synchron conditions for the fast transfer mode. Then it's not allowed to give the commands to both breakers simultaneously. We have the two aims. We want to keep all the loads on running, but also we want to protect all the loads. So that means if you make, you can imagine if you make a transfer, maybe in phase opposite between phase opposite bus bar voltage to standby feeder voltage, and you make exactly at this moment a transfer, then you can imagine you will break some mechanical elements on your motors, on your gears, or something else. This will be very dangerous. It will be absolutely avoided by HSTD. And that's why only to this window, to this preconditions with the 20 degrees, 1 Hertz, 70% of nominal voltage on the bus bar and 80% of nominal voltage on the standby feeder, then it's allowed to perform the fast transfer. So, for example, we have not the conditions for the fast transfer. The device measures all the time in the network and knows that we have not the conditions for the fast transfer, and the device get initiation signal. Then the device tries to fulfill the next fastest transfer mode, and this is the transfer at first phase coincidence. In this example, the failure happened, initiation signal comes, device has made the decision before, okay, fast transfer mode is not possible. Then the device sends the command to the incomer breaker, open. Only open, not closing the standby feeder breaker, only open to disconnect the failure from the bus bar. And then the breaker is opened. And then we start this, the motors are running with high speed, they're declining, and also to this declining, the frequency changes. So, I would like to explain it here. In this moment, see here, feeder 1, the main feeder will be disconnected, and the bus bar is isolated because the standby feeder will not close. We close the standby feeder to a special moment. And this will be explained here. We have this phase angle from the standby feeder, and we have the phase angle from the bus bar. This is more than 20 degrees. Okay, fast transfer, it's not allowed. This moment, the breaker is opened. You see no more current on the main feeder. Breaker also from standby feeder is not closed. The voltage on the bus bar is declining, and also the frequency goes down from 60, 40, 50 Hertz, goes down. In this moment, in comparison to the standby feeder, to the bus bar, we get a phase angle. And you see this phase angle is rotating, and after a certain time, we have once more a short moment when they are in synchron conditions. So what do the HSTD in this moment? The HSTD can exactly calculate during the measurement on the declining voltage on the bus bar and the network the speed of this phase angle. Very exactly. Even the speed is going down, going up, we can calculate. And according to calculate the speed of this phase angle, the device can make a prediction at which time they are once more in synchron condition. So, and now I'm step back a little bit. During the commissioning of such a device, the breaker time for opening and closing will be measured exactly. That means not from the auxiliary relay in the breakers. It will be measured by the current when we send the command from this device to the breaker up to the time the breaker really physically opens. And then we know exactly, and the device also know exactly how long the breaker needs to close or to open. And we need it for this transfer mode, because the device calculates exactly the speed of this phase angle, which is going around the standby voltage. And the device knows exactly, for example here, from here to one small synchron condition, we need 50 milliseconds. And also the breaker needs to close also 50 milliseconds. Then the command to close the standby feeder breaker will be given in advance before they once more meet the synchron condition. So the HSTD knows exactly the speed of this phase angle, knows the time for closing the breaker, and then the command will given in advance that the breaker physically closes in the moment of synchron conditions, and then the bus bar is fed again. This is the next transfer mode if the fast transfer is not possible because the preconditions are not given in the moment of initiation. Then the HSTD performs not in fast transfer, goes to the next possible transfer mode. This is the transfer at first phase consonance. And you can also imagine if we make the change over the transfer in the moment of absolutely synchronism, so this is a really smooth transfer. And normally you can say the bus bar voltage is declined to, it's depending on the application, to kind of voltage where also all the loads keeping alive. So here in the moment of changeover will be here 70%, 65% of bus bar voltage at the end here. They're declining from here 100%, maybe 90, maybe 80 to 70, and then we have this first phase coincidence and we can make the changeover. So if the fast transfer mode is not possible, then the device tries to perform in first phase coincidence. So in some cases, it could be that the disconnected voltage, the disconnected bus bar, the voltage on the disconnected bus bar looks like this. The bus bar is isolated, the voltage is declining, but the differential voltage between bus bar and standby feeder is not calculatable. So it makes steps, the phase angle goes faster, goes slower, goes faster, and a prediction of this phase angle is not possible. Then we have not the chance to perform in the first phase coincidence, because we cannot make this really exact prediction from this phase angle up to synchron conditions. That means both phase angles in the same direction. To perform the transfer is here not possible. You see it on the differential voltage. Then the device makes also the decision, okay, it's not possible. Also here, like in the first phase coincidence, the main feeder breaker always will be opened. The failure must be disconnected from the bus bar immediately, always. Then we wait, we see, okay, first phase coincidence transfer is not possible because the speed of the phase angle is not calculatable. In this moment, the device says, okay, I step over to the next possible transfer mode. This will be here the residual transfer mode. And in this transfer mode, we wait until the bus bar reaches a certain kind of voltage. Normally, it's 40%. And if 40% is reached on this bus bar, then the standby feeder breaker will be closed to feed everything again. Yes, frankly speaking, if we go down to 40%, then you will lose some kind of your connected loads. But this is only the transfer mode if fast transfer mode was not possible, because it caused, for example, by a very old protection relay with a big filter time, needs a long time to detect the failure, gives the information to the SOE, the command to perform the transfer too late, and too late means the phase angle is maybe more than 20 degrees, or the busbar voltage is declining to 50% or something else. If you have a good protection relay, a fast protection relay, means also protection relay state of the art today, then you will have always the chance to have the fast transfer mode. Normally you have always the fast transfer mode. And only if this is not possible, then normally the transfer will be performed at first phase coincidence. This is more or less like a backup. If everything failed, the protection was too slow, and you have these problems on your bus bar during this declining, you cannot measure the phase angle speed because it goes slower, faster, can be caused by other commands from load shedding signalization. That means we have certain kind of load sheddings during this declining, and then to every kind of load shedding, the phase angle makes a step or go slower or go faster, and then this could be caused. Normally you have always fast or first phase coincidence. This is more or less a backup. So why 40%? I say, okay, we're waiting to a kind of 40%. I would like, don't be confused, I step back to this one here to explain why 40%. So we're reverting only to 40%. So we don't have a look on the phase angle anymore. We say 40%, make changeover. What is the worst case in this moment? Yes, 40% with a phase angle in phase opposite with 180 degrees. Could be. We're waiting to 40%. We don't care about the phase angle, where it is. Is it here? Is it here? Is it here? Could be worst case in this direction. Then you have a complete voltage, if you close the breaker, of 1.4 of the nominal voltage on the bus bar. So 1.4, you can ask all the manufacturer of mechanical components, motors, gears, or something else, a hit of a voltage of 1.4 of the nominal voltage, it's always accepted by them. And if you have special mechanical elements and the supplier says, oh, 1.4 not possible, do it maximum with 1.3, we have very sensible gears or something else included, then such settings can be made in the devices. So if I say 30%, this is very common, but if you need other values and settings, then this could be changed. But 40% is always accepted and used in all kind of industry and power plants. So even there is a phase opposite in this moment, it's no problem, because we are waiting up to 40% for this changeover, then it's no more problem. So I will go back to this residual voltage. So normally, yes, fast transfer, then first phase and residual voltage. And we have a very last one, it's a time-depending transfer. So what happens if you have a failure on the main feeder, and in the same moment the voltage transformer is also blown away from the bus bar information. So you have no more information of the voltage from the bus bar. The SOE cannot, the HSTD cannot perform the fast transfer. Why? Yeah, okay, for the fast transfer we need 70% of bus bar voltage. If we have no information, transfer is not possible because we need this information. Transfer at first phase coincidence. Also, we have to compare the synchronism between standby feeder and bus bar voltage. If we have no more information from bus bar voltage, also not possible. residual voltage, we have to wait until 40% on the bus bar. If we have no information, we can also not perform this one. This is a very special failure. You see, you have the failure in the main incomer, and at the same time, the voltage transformer is blown away from the bus bar. But everything can happen. So in this moment, we have no more information of bus bar voltage. We cannot perform one of these three transfer modes. Then we do it in the time-dependent transfer. That means if we get the initiation signal and have no more information about the bus bar voltage, then the device will perform a transfer after, I give an example, 2 or 3 seconds. After this time, this will be measured also by the commission. You will see all the motors running down, going down on the bus bar, everything has a still stand. We send some load shedding signalization because, you know, if everything is connected going down, you open the main feeder breaker and it's closing the standby feeder breaker after 2 or 3 seconds with all connected loads. That's not possible. You cannot start all the connected motors at the same time. Then we send also load shedding signalization that only a few motors are still connected or nothing. But after this 2 or 3 seconds time-dependent transfer, the breaker will close and you can manually start all the loads once more again. Okay, for sure. Time-dependent transfer is like an ATS. And with this transfer mode, it's not a transfer mode, it's really like a backup. You have the failure in the main incomer and the blown voltage transformer. That is the same functionality like an ATS. After a certain time, close the standby feeder breaker that you are able to start your whole protection again. That's also a quite good transfer because yes, at which time you have this failure in the main incomer, yes, at the night and especially on the weekend, and the maintenance team are only a few guys and nobody is allowed to make to disconnect or close or open breakers in the medium voltage switchgear or something else. They have to call someone. It's not necessary. Here, at latest, after 2, 3, or 4 seconds, the changeover will be done and all the maintenance guys can start again the production line, and nobody needs a responsible person who is allowed to make to give commands to the breakers in the medium voltage switchgear. So this was the overview from the SOE. We seen the transfer modes. This was the declining voltage on the bus bar. This was the phase degree between standby voltage and bus bar voltage. And after 360 degrees, you see here phase degree. After 360 degrees, we reach this window for the fast transfer, for the transfer at first phase coincidence. And remember, we calculate exactly the speed of the phase angle. We give the command advanced that the breaker will be closed exactly in the moment of synchron condition. It means no phase angle and the breaker closed at this time. If you would give the command in the moment when they're in synchron condition, and then give the command, then it needs about 50-60 milliseconds to close the breaker, and then we have once more a phase angle of maybe 20, 30 or 40%, and that's not the aim of the SOE, of the HSTD. We want to close the breaker in the moment of absolutely synchronous condition, that you have a very, very smooth transfer without a big inrush current or something else to make a mechanical torque hit on the elements, on the motors. Makes very smooth. Then the residual, if this is not possible, this is like a backup, and this is for the last possible thing, failure in the main incomer and also blown away. But normally you have always the fast transfer. This is the main transfer mode if you have a good protection, if you have breakers below 100 milliseconds, and then you have fast transfer mode, and with this fast transfer mode you keep all the processes alive. This is the big feature from HSTD, to provide this here, this here, this here, and if you see this is made the functionality of an ATS. And you can see now the big differences and the big technology of such a HSTD. This is the ATS, and this all together is the HSTD, with this functionality. And here we keep everything alive, and with this functionality of the ATS and called for the HSTD time-dependent transfer, you will lose everything on your bus bar, on your processes, and have to restart everything in your facility, in your industry, and takes some hours up to a day, and you have big trouble until everything runs again very well. So that you get an idea when we're talking about transfer. So this is only if you use some special breakers. Don't look at this. Normally a fast transfer, if you calculate a little bit, if you see, okay, a good protection relay detects a failure in, I would say, good 20 milliseconds. Then a HSTD needs about internal time of 10 milliseconds. And a good breaker, well, we said, okay, worst case is the closing time is 60 milliseconds. So we calculate all together. 20 milliseconds for the protection relay, detect the failure, give the information to the SOE, means the command, please perform the transfer. 10 milliseconds for such a HSTD, then we are at 30 milliseconds, and 60 milliseconds for the breaker. Then we have 90 milliseconds. Within 90 milliseconds, in fast transfer mode, we finish the transfer completely from the failure in the incomer, in the main incomer, up to the standby feeder is closed. And please remember, during this 90 milliseconds, we have not a zero voltage on the bus bar. We have a high voltage. We have this feedback energy from the motors which are connected, which stabilize the bus bar voltage. And in this example, you have seen during the transfer and also during this gap, you have no interruption on the bus bar voltage. Transfer at first phase coincidence, yeah, depends a little bit how fast this phase angle is rotating, how fast we get synchrone condition once more. This is depending a little bit on the application from the motors. Are there pumps or fans or something else? Takes about 250 to 500 milliseconds depending on the motors and the application. But always also after the first phase coincidence, means one cycle around, you have a very high level on voltage on the bus bar. So the residual voltage also is depending how long the bus bar is isolated, the motors are feeding back. If there's really big motors and they're running a long time, then it takes also a long time until the bus bar voltage is declined to 40%. If you have small motors or pumps, they are nearly stopped immediately, and then you reach the 40% very fast. And the time delayed transfer, yes, this is a setting. The setting will normally take into account how long does it need until all the motors are stopped on the bus bar, and then make the change over, that you can be absolutely sure that nothing is working, that nothing is rotating, that you absolutely avoid a transfer in this moment if the bus bar voltage is not below 40%, because we have no more information about the bus bar voltage for the time delayed transfer. Then the voltage transformer is blown away. So this is a short overview that you get some feeling for the times. Yes, normally fast transfer below 100 milliseconds according to breaker and according to the protection relay which is existing. And remember, we have here always a high level on bus bar voltage during this feedback power. First phase coincidence, also here you in most cases you keep nearly all processes alive. Here with 30% you will lose a lot of process, and here we lose all the process. But normally you have always the fast transfer mode, and only if this is failed, then you get the first phase coincidence transfer. So this is, I would say, 99.9% of all transfer modes, and here it's 99.5. It's the normal, this is standard case for the transfer. And this is the really good thing for HSTD. You have no more this downtime to restart everything, no more this trouble, you know, all this trouble if there's a power interruption and you have to start everything again. There's a lot of trouble, and with this device, this trouble is in the past and you will have no more. So, we are nearly at the end. What we have discussed, yes, we have discussed the general applications for the HSTD, and the main task. Yes, the main task is to keep everything alive. The difference to an ATS, yeah, ATS is, I would say now, a stupid device, opens only the main feeder, waits a certain time, then closes the standby feeder. That's very easy, but you have really no benefit. The necessary components, yeah, you need state-of-the-art protection relay. You need breakers with opening closing time below 100 milliseconds. You have seen the construction of the device, how it looks like, the interfaces. You only connect to the breakers, to the protection relay, to the voltage transformers from main feeder, standby feeder, and from the bus bar. It's very easy to integrate into existing or new switchgear, so it's very easy. You have seen the different variants, so variant 1 up to 5, to different kind of switchgear configuration, so it means with one incomer, one standby feeder and a common bus bar, or two incomers with a bus bar coupler and two bus bar sections, or two possible standby feeders, and all the different kind. And the main thing, how the HSTD works, the different transfer modes. Yes, we discussed the fast transfer mode. The commands are given at the same time with this only small gap of a few milliseconds. The bus bar voltage is stabilized by the rotating machines. We have the first phase coincidence, the residual voltage, and the time delay to the transfer mode. So this is explained, and I hope so. You get a little bit feeling now about such a HSTD and the technology behind, and the big difference to an ATS, and also the big benefit you got with such an HSTD, that the transfer is performed so fast, and also we have the device have a look to secure also the connected loads to avoid any damages or problems to this. So we make the transfer so fast, everything keeps alive, and also have a look on all these components that nothing will happen to them. Okay, so we are now at the end. I hope so. Yes, I explained it in a way everybody can understand. Sometimes it's not so easy if you have not an audience in the front and they can ask the questions. Thank you very much for your time today, and wish you a nice rest of the day. I think now it's the local time, USA, it's 1 o'clock, and now I would hand over once more to my host. Thank you very much, and may hear you at the next time for other webinar.
Thank you very much, Uwe. That was a great presentation. If anybody has any questions, feel free to either raise your hand or enter them in the questions pane, and we can ask you that. Or if you would like, I don't think, Uwe, did you have an email that you would like to provide?
Yes, for sure.
Do you want to just advance to the next slide?
What shall I do?
Advance to the next slide.
Yep. Okay.
Okay. Thank you, everybody, for your participation. Shortly, you will receive a link to an archive of this presentation, and we will also provide you with emails there, so that way you can send them any questions you have. To view a scheduling of remaining webinars in the series, or for more information on ABB's protection and control solutions, visit abb.com/relyon. Please join us in our next webinar session, which will be on July 26th. It's Digitizing Copper, Applying IEC 61850. process bus to optimize protection and control designs. So I don't see any questions at this time. Thank you, everybody, for your time today, and have a great day. Thank you, Uwe.
Thank you. Thank you.